So probably let's just begin. Yep. So I hope everyone can see the screen. Um, as mentioned before, basically I'm just covering the book by Schut and Petrosian on machine learning and quantum computing, something like that. The title for the book. So today I'll be going into the second chapter, which is on machine learning. I'll be covering the first two sections. I'm not a computer scientist, by the way, so if I say anything wrong, please correct me. Yeah. So basically, for again, just to restate why I do this. Basically, I want to learn quantum machine learning, and then I think just me reading the books and then sharing what I learned from the book, I think is it's not just useful for me, it's also useful for everyone who wants to learn, uh, who wants to read the books together. So, which is why I do this so-called journal club. So, for chapter two, basically they try to formalize what is machine learning. So, there are a few things that the book tries to avoid because AI or machine learning is a very wide topic. So just to introduce a little bit, AI basically are computer systems that are good at human-like tasks. Like you can reason with it, you can try to navigate whatever problems or questions that you want to ask, and then you can interact with it. I believe we have some experience with AI ourselves. So you can try to think of machine learning as a subset of artificial intelligence, whereby we just want to learn the pattern and basically you provide a set of data without any physical laws or like equations or relationships with it. And then you are trying to use machine learning to study what are the patterns in the data and then try to make predictions if let's say you are given the next time step. So whatever we are trying to learn, usually the pattern is going to be very complex, which is why we feed into machine learning in the first place. Oops. um and then we don't really understand what is happening with the data, like what are the relationships, because usually they involve a very large degree of freedom that we might not be able to capture with our theories. So which is why we use machine learning. And of course it's kind of difficult for us to come up with a model of whatever equations that we want to model with the data. So that's why we use machine learning. So usually in machine learning, you start with a very general and agnostic model, and then you sort of like feed some data into the machine learning, train the model until at one point the model sort of like fits all the data that you have. And this whole process is what we call as training. If you are familiar with machine learning or at least use a little bit of it, then probably you understand what is going on. So because we are only trying to learn the relationships of the data without really understanding what is the physics or like the relationships happening behind the scenes. So you can consider machine learning as a black box, whereby you don't know what is happening. You just know you feed in the data inside, and then you can produce some reliable outputs, but you don't know what is happening inside, right? And this is the biggest criticism against machine learning or even AI tools in general, because you don't know what is happening inside. sometimes when the machine learning or AI gives you a certain output or a certain decision, you are not really sure why they make that kind of decisions. But if you think about it deeply, this is also the advantage of machine learning or AI, because you can feed in whatever data you want, and they will give you they will just study the relationships of or correlations inside your data, and they will give you the output. So it means that your machine learning model can be very general, and it can be applied to a huge variety of tasks across different domains. And some of the domains, like stock market, for example, predicting the oil price for tomorrow, like these kind of applications are very useful for the whole world, which is why AI or machine learning took place almost immediately. Also, to counter this weakness, like you have a black box that you don't really understand what is going on inside, there is a research field called explainable AI, or you can call it interpretable AI or explainable machine learning, which sort of like tries to explore what is actually happening inside the black box, so that you can sort of like understand uh, like what is the reason the machine learning model actually make those kind of predictions. So one thing that I recently if you heard of there is this one, I forgot which interview with, who is that guy again, Terence Tao. So he was one of the advocates for using machine learning or like AI tools in mathematical proving. So there is this very interesting point of view that he mentioned, that um, is actually we are not like the first time doing this kind of things. Actually, in the past, Kepler's, when he formulated the laws of planetary motion, he actually studied the astronomical data by Tycho Brahe. I hope I pronounced the name correctly. So so through the data coming from this guy, he formulated the laws without really understanding what is the physics behind. So it is only later, when Newton derived the law of universal gravitation, that we sort of like understand how gravity works, and how you're actually deriving this Kepler's law. So in a sense, we are applying machine learning um, in a historical setting, but by human, of course. So now, if you think about what is machine learning, basically, it's the same thing. Something very complex that we don't really understand what is happening, and we are just feeding in data and trying to understand the relationships. But maybe in the future, we will be able to, I don't know, formulate some equations for that particular system that you are trying to study. So that's one point that he's trying to make. And I think the argument is basically that you basically can use machine learning to feed in whatever data that you want and get somewhat accurate predictions. But what is lacking right now is the human that actually tries to formulate the equations or the principles, or what is happening behind. So that is his argument basically. So in this book, they will only focus on two types of machine learning. One is supervised learning, another one is unsupervised learning. So what is supervised learning? Basically, you start with some labeled training data. So what is this labeled training data? Basically, you have some input and output pairs. Like for example, if you have image recognition as one of your supervised learning, so what you actually need to fit into your machine learning model is basically you first start with all these different pictures, like this picture means flower, this picture means dog, this picture means plane, and so on and so forth. So this kind of data you fit into your machine learning, and then you want to predict, let's say if I give this particular image, so what would be the label of this image? So basically, this is one way you can use machine learning in the supervised learning scenario. So in this sense, you have so your data will have two labels. One is a picture, another one is the name of whatever the picture is. So in this case, you are just giving the picture, and then you want the machine to actually answer this is a cat. So this is one example of supervised learning. Another supervised learning example will be time series forecasting. What is a time series? Time series basically is a set of data whereby you have some values coupled with the time intervals. So a few examples would be, for example, stock market, oil price, um, maybe weather. So you have some values, like weather, for example, you will have the temperature and then the timestamp. So it's very similar to this one, whereby you have a label and then you have whatever measurements that you are trying to make. And then the thing is, for example, weather, the data points would be so complex. Like there are so many different factors affecting weathers. There are so many different factors affecting your oil price or like stock market. You are not likely to capture all these different variables into your data, and which is why using machine learning can help you to predict what is going to happen in the next time step without really understanding all these different factors uh, that can affect whatever data that you try to fit into the machine. So these are the two examples of supervised learning. What will be unsupervised learning? You are just given a data set and it doesn't really have labels. So you just give your machine a set of data without any labels. And then you try to identify what are the patterns or the structures in this unlabeled data set. So one good example coming from the textbook is what we call as hypothesis guessing, whereby the scenario would be like this. So you have a candidate that you try to give the person a list of integers between 1 and 100. So for example, the data set that you are giving to the candidate is 4, 16, 36, and 100. So now the candidate has to find a hypothesis that supports these four numbers. And with the hypothesis, you can predict what will be the next number. So if you want to do that, you have to find all the different patterns coming from these four numbers. So you have to guess what are the rules or the hypotheses that is valid for these four numbers. Um, so coming from this example, there is actually so this example actually comes from this guy's PhD thesis. It's basically a hypothesis telling I have not complete all this reading, but from what I understand, basically it's trying to model how human learns. So there is this process called Bayesian hypothesis testing, whereby the concept would be like this. So let's say you have three hypotheses. So the first hypothesis is even numbers. 4, 16, 36, and 100 are even numbers. Or you can try to think of it as multiples of 4. Or you can also think of it as power to the 2. So you have these three different hypotheses, and what the assumption is taking is that it is way easier, and if you think about it from the probabilistic perspective, it is more intuitive to select the hypothesis that fits all this data, but you also have a smaller amount of options. So, like for instance, if you look at hypothesis one, you have so many different numbers, and the coincidence for you to choose these four numbers out of all these possibilities is really high compared to hypothesis 3. So for hypothesis 3, if you want to select these four numbers, uh, relatively speaking, you are not choosing these four numbers by chance. It's more likely to be uh, the hypothesis 3 to be true compared to hypothesis 1. So this is basically what the whole idea of hypothesis guessing is talking about. So basically, that's what it is. So based on this, then you would say that hypothesis three is the most likely to be true for these four numbers, and you should use hypothesis three to predict the next number. So that's one of the examples of unsupervised learning. So in the textbook, they also mention other different tasks of unsupervised learning would be, for example, trying to study how the data is clustered and how are you going to reduce the dimensionality of your data. So the third type of learning, which is not covered in the textbook, is what we call as reinforcement learning, whereby you have the machine, also known as the agent, to play a game. And I think this is quite a famous example. You play Go, for example. So you have a set of rules given to the agent, and then you try to give rewards or punishment according to whether or not this is the next best move or not. So by trial and error, the agent will learn what is the optimal strategy to win the game. Usually, you don't really start from zero. Before you even play with the real player, you kind of like feed into your agents a lot of history strategies so that he can learn through that, and then uh, you play with the real person. So that's roughly what is a reinforcement learning is. And the last one is called the deep learning, which is a technique to perform machine learning based on how our brain works. So basically, these two we are not going to cover in the textbook. So the board games will be the example for reinforcement learning. If you want to know what is the example for deep learning, you can consider, for example, neural networks, convolutional neural networks, and all that. So those are deep learnings. So basically, you are applying layers of neural networks to perform your deep learning. So what would be the ingredients for machine learning? To formalize the definition of supervised learning tasks, basically, for supervised learning, you are given the input domain and the output domain. And okay, I think there is something here which unfortunately LaTeX did not capture. So basically, your dataset consists of all the points x1, y1 until X capital M, Y capital M. So this is your data set. So your X will be your input, your Y will be your output. Um, so this is basically your samples, and it can be coming from a probability distribution. And then lastly, you also need to have some unclassified input X. So after you learn through this data set, you are going to predict with your model what is the corresponding output Y. So this is what a supervised learning is going to do. For unsupervised learning, basically you are just given the input domain, and basically your X will be your data sets. And what you're going to do is to uh, create or sort of like sample the probability distribution, and then coming from what you are trying to guess about the probability distribution, you try to draw new samples coming from this distribution. So that will be your unsupervised learning task. And your machine learning will always try to solve problems by defining what we call as a model family F. This you can just think of it as a set of functions that maps your input. If it is a supervised learning task, it will map your inputs from your domain X to your output from domain Y. If it is unsupervised, then it will be just giving you the probability distributions over your input X. So that's basically the definition for supervised and unsupervised learning tasks. So also for supervised learning, usually you need to pick a best model to reproduce whatever data that you have. So this procedure sometimes is called risk minimization. Basically, you are trying to define what we call as a loss function, and then you try to measure what would be the difference between what your model is going to predict, which is f of x, versus the real output, which is y. So over here, I haven't really discussed what would be the practice for machine learning, like how would you divide your data sets into parts so that you have one data set for you to train, and then you have another data set for you to verify before you actually go into the real machine learning. But right now, you just think of it as these are the more general procedures. So of course, your best model is the one that minimizes through your loss function uh, over all your possible data. And the challenge for supervised learning is basically if let's say you are coming with a very limited samples, so how are you going to use those limited samples and model the entire domain of your data? So that is the challenge. For unsupervised learning, basically you don't really have a loss function because you don't really have something to compare, because in the end you are trying to model the probability distribution. But there are also ways for you to do it, which we will briefly discuss later. So basically, what you can do is to consider your probability distribution as something like a set, and then you try to measure the distance between your probability distribution. But usually, I think this is coming from the textbook. Usually, what you do is to convert your unsupervised learning into supervised learning so that you can use the loss function from supervised learning and find the best model. Also, for your machine learning model, they are typically parameterized, meaning that you have a set of parameters that you need to optimize, so to say. So then your machine learning models can be converted into an optimization task whereby you try to optimize each of these parameters that you have to get the minimum values for your loss function. So that's usually what would you do in a machine learning task. So one example would be like this. So let's say this whole class A and class B, uh, all of these are your data, but for training, you only have access to these four data. Okay. So then you go through your model and you sort of like formulated three hypotheses, F1, F2, and F3. So let's say F1 says that if a row or a column is filled, then it is class A. Otherwise, it will be class B. F2 will be if two blocks is filled, then it is class A. Otherwise, it's B. F3 will be if no block is filled, then it is A. Otherwise, it's B. Okay. So these are the three hypotheses that you may formulate when you formulate your machine learning model. And then you try to perform your loss functions with only these four training data sets. So empirically speaking, if you compare your RIX function, you'll find that F1 and F2 basically satisfies sort of like these four data because okay, F2 basically there is no errors, so that's why it's 0 over here. F1 is the same thing. So then these two hypotheses based on these four training data, basically they are of the same power. But if you consider the whole data set, you start to realize that class A actually means that your whole row or your whole column actually has to be filled. Class B would be the otherwise. So your expectation is that F1 is the perfect one, F2 is not so perfect, then F3 is the wrong hypothesis. So this is what you would expect, but because you only have access to a very small training data, so over here when you try to perform your machine learning training, you basically have F1 and F2 to have the equal amount of errors, so to say. So this is one of the challenge of machine learning because you only have access to a very small training data set compared to, for example, the whole data set. Sorry. So for supervised learning, you can further differentiate them into two different tasks. The first one is called classification. The second one is called regression. What we did just now is basically classification because each of these data is associated with a class. So this four data set has a label class A, whereas this one you have another label class B. So your hypothesis is trying to classify giving, let's say if I give you a data, a block, you need to classify into class A or class B. So that's what classification means. Um, so if let's say you have a set of outputs with some discrete class labels L1 until LD, then this is definitely a classification task because like just now, you only classify into class A and class B, but in reality, you can have multi-level classes. And this multi-class classification task, just remember that you can always reduce it to binary classification. The way for you to do it is basically um, you first try to consider, let's say, L1 and then the rest of the class. So you convert your multi-class classification into binary classification, L1 and the rest. After you compare between L1 and the rest, then you compare L2 and the rest, L3 and the rest, and so on, until you reach to all the different classes. which is why over here they say that you can always reduce it to binary classification. Whereas for regression, basically you are trying to, for example, fit into a straight line, linear regression, or fit into a quadratic line, and so on. So it refers to problems where you try to predict what is going to be happen for your output. And one of the assumption is that it has to be continuous value, and it doesn't really need to be a probability distribution because line regression exists. So over here, even though you sort of like differentiate your supervised learning into two different tasks, your classification task can be converted to regression and vice versa. How you can do it is by so how are you going to switch from classification to regression? You need to change it to continuous variables by adjusting your functions and distribution accordingly so that you can change it to regression. And if you want to change from regression to classification, then basically you just need to set, for example, certain values. If let's say your f of y exceeds certain values, then it is of class 1. And if it is smaller than a certain value, it is of class 2. So that's how you switch between these two different tasks. Basically, what the textbook tries to tell you is that even though you have differentiations between different machine learning tasks and different types of machine learning, like supervised and unsupervised machine learning, it is always possible to convert between one another. That's what the textbook tries to say. So we covered the first part of your machine learning, which is you have different machine learning tasks, and then the general flow of it, and what kind of tasks exist in your supervised learning. So the next thing to discuss is the first ingredient, which is called your data. So one of the assumptions for your data set, this is not usually being discussed, but you have to assume that your data set is clean, meaning that it has to be independent and identically distributed. Of course, in reality, this is not the case, but this is the assumptions that we try to make so that you don't want to deal with not independent data sets. So then your domain X, you can assume it to be in the vector space of Rn. Then all this data becomes what the feature vectors inside this vector space Rn. So in some cases, like just now you see the image recognition, your raw data is not from a numerical domain. So what you need to do is to find a representation for it to become a numerical domain, and then you convert it to vectors before you can perform your machine learning. So your data is often pre-processed just to improve your the power of your machine learning algorithms. So there are three different ways for you to do it. The first way is the feature selection. You select the features that you actually want to study or want to learn. The second thing is called feature scaling. For example, if your numerical values is too large, then you would want to uh, narrow down your numerical values. Let's say your data is in the millions, then you want to scale back so that it's easier for you to study, or you want to convert it to normal distribution. So these are all the statistical transformation that you can perform. The third one is called feature engineering, meaning that you have a lot of different data sets, but they are relevant to each other, and you try to combine all these different data sets into a single one so that you have a stronger data set that can actually tells you meaningful relationships when you fit into your machine learning models. So the second thing would be talking about your models. So what is your models? It can be a function, it can be a probability distributions, it can be your algorithms, it can be any rules that will help you to reproduce either your data sets or the probability distribution of your data set. So there are two types of models. The first one is called deterministic model. The definition will be like this. So basically, again, this definition is for supervised learning. You have input domain and output domain, and your deterministic model basically gives you a deterministic function for your prediction. So notice that x is coming from your input. So this is f of x. So f is your model. So f of x is actually your prediction. Y is actually coming from your real data. So of course, your deterministic model, of course, what we hope is that whatever prediction that we make is exactly whatever the output coming from a data set is. So that is our aim. So as mentioned before, your model can depend on a set of parameters. So in this case, if let's say it depends on a set of data parameters, then you define what we call as a model family. There is also what we call as hyperparameters that can give your model family additional degrees of freedom. So at this point, the textbook did not really define what is hyperparameters. Just as an example, you can think of your hyperparameter as, so if you consider the example that we covered in the last discussion, the nearest neighbor example, the nearest neighbor method, we use a square distance. So the distance measure is your hyperparameter. I suppose when we go into the machine learning models, then we know more about hyperparameters because this is also important for quantum machine learning later on. So for now, let's just keep it as it is. So the second model is what we call as a probabilistic model. So for probabilistic model, it can be supervised learning. It can also be unsupervised learning. So if it is supervised learning, of course, you are going to have input domain and output domain. So what you are going to produce is the probability distribution that will give you back whatever the pairs of input and output that you try to learn, or it will give you a conditional distribution given that your input is x, what is your output y. So these are the two possibilities for supervised learning. Whereas for unsupervised learning, basically you are trying to model the probability distributions. So then your p theta of x would be exactly the model that you have, and that's it. So a probabilistic model, you have two ways to work. The first one is what we call as the density estimator. It defines an actual function that computes the probability of a data sample. The second one is what we call as a generative model. So for generative model, you start with a deterministic model, for example, and then you add noises and into it, so that whatever deterministic results that you get starts to form a distribution. And that is the basis for generative adversarial network machine learning model. Again, right now we don't really explore too deep into these two things. So let's see the next few sections whether or not they will talk about this more. But when you model your probabilistic model, basically you want to model it into the distributions that we are all familiar with. The first one is, of course, the normal distribution. Uh, then your parameters or hyperparameters will be your mean and your standard deviation or your variance. If you model it into a Bernoulli distribution, then basically your hyperparameters or parameters will be your probability of winning, which is denoted as Q over here. So, like I said, depending on the context of your problems, your parameters can be identified as hyperparameters. So at this point, we are just covering all the ideas in a general way without going too deep into examples. So again, you start to see a very similar pattern. They try to tell you that probabilistic model can be turned into a deterministic model if you provide a rule for you to derive the deterministic output. So two of the rules, either uh, you try to find the maximum of your probability distribution, or you try to find the mean of your probability distribution. So how are you going to read this conditional distribution? So if you are learning or modeling a supervised probabilistic model, what you are going to produce is actually this whole manifold thing. And what this conditional probability distribution is basically trying to fix your x, and you look at what is happening to your y. So in this case, your conditional distribution basically is your marginal distribution, whereby you try to cut a slice onto this whole manifold thing, and coming from this slice, this will be your distribution. Then coming from this distribution, you can either use your maximum, or you can find the mean of this. You can find the mean of this distribution, and you turn your probabilistic model into a deterministic output. So that's how you can do it. So lastly, what we actually need is also the loss function. So it is a measure of how close your model tries to predict with whatever targets that you want to get. So for supervised learning, basically you have all these different methods. If you are sort of like classify stuff, then your accuracy can be defined as how many times you correctly classify the samples versus the total number of your samples. The mean square error is probably the one that we use the most. You can also define the L1 mean. Hinge loss and logistic loss, I have no idea what it is at this point. Usually, what I encounter is either two or three. So I will have to look at further examples from the textbook in the later sections to be able to say anything meaningful. But this would be the loss functions that you can look at it from the graph perspective. So for unsupervised learning, as I said, because you are trying to model the probability distribution, it's harder for you to judge what is the quality of your model. Again, like I said before, if you there are ways for you to overcome that. So two possibilities. If let's say the models gives you the exact form of your probability distribution P of X, then you can try to use information geometry and identify the likelihood between these probability distributions to sort of like see how your observed data is coming from your probability distribution that is modeled by your unsupervised learning. If let's say they only give you samples, they don't give you the distribution, then you will have to turn your unsupervised learning into supervised learning. So now you need to add in the label. It's sort of like just now what I said. You sort of add in another label saying that whether or not this data is coming from the model or the original distribution, then it becomes a classification task. And then because you turn it into supervised learning, you will be able to use the loss function stated before. So over here, you can see the left hand side will be your supervised learning. So these are two different tasks. The first one is regression. So given all these different points, what would be, for example, the line of best fit for this point? So that is regression. So then how are you going to measure the quality of your regression? Just measure the distance, for example, over here for each point, and then find the minimum. This will be classification. So it's either on top or on the bottom. So again, how are you going to measure is to perhaps define a middle point here and then identify the distance of your point to let's say a middle point that you want to define, and then so on and so forth. So for unsupervised learning, you are producing only results on your x-axis. So your y-axis is actually your probability distribution. So in this case, it will be harder for you to define your loss function unless you are given the probability distribution model based on your unsupervised learning. Then you can compare. Otherwise, you have to turn into supervised learning. So up until this point, I basically covered the first two sections of chapter 2. The next two I will cover in the next discussion, the next two sections, because it will sort of like fit in to all the different classical machine learning tasks, like all the different methods. Uh, I will stop the recording first.